Hi everyone. Today's lecture is going to be focusing on locks and how they are used to control synchronization between both processes, I guess, and specifically between threads. Now, part one will look at why we need locks, as well as what a lock is in the first place. While part two will look at some different types of locks, as well as their actual implementation. But before we get into that, just a quick recap on what we looked at a couple weeks back. We basically discussed what is concurrency, and that was the idea that you can have multiple tasks running at the same time, just like how multiple things are occurring in the same time in the real world. We looked at how threads allow for concurrency to occur, as well as like multiprocessing. And we looked at the thread API and how it was very similar to basically our process API in terms of like thread creation versus process creation, yielding, the termination or exiting of a thread. And we also looked at the thread lifecycle where we have those ready, running, all those different states in that state diagram and how those transitions occurred. So moving on to today, we're going to be discussing how sharing objects impacts our concurrency and how it impacts correctness as well as control in terms of our execution of a process. Now, as the slide says, if a program has independent threads that operate on completely separate subsets of memory, we can reason about each thread separately. And that's because, well, since these threads don't interact with each other and they perform completely separate tasks, it's pretty easy to predict their behavior. The problem is most multi-threaded programs have both a per thread state, and this is what we discussed as well last week, and this per thread state was made up of our stack as well as any registers pertaining to that specific thread, as well as that shared state, which was the heap. And this shared state is what causes us a little bit of problem, because this heap now is shared across multiple threads, which are basically like multiple processes, which can each interact with that heap by changing values, by adding values, by basically manipulating it. We have what we call control problems through that manipulation of that heap. Now, threads which can read and write to that shared state are called cooperating threads, and obviously the opposite to this definition would be non-cooperating threads, for threads which cannot utilize this shared state. Well, like I alluded to already, when we have cooperating threads, it becomes a lot more difficult to write correct multi-threaded programs. And by correct, I'm talking about a program whose processing or execution produces a correct output every single time, or a valid output every single time. Now, the reason this is much more difficult with cooperating threads is because of a couple different cases, such as our program execution depends on our scheduler, or the possible interleavings of threads which access this state. Now, the idea here is, well, what if one thread changes value X that's on the heap, and later on another thread changes value X? Well, the ordering in which these two things occurred might change the output of your program. And because of that, program execution can become non-deterministic, meaning that we can't predict exactly what the output is going to be every single time. And additionally, compilers and processors, or the processor hardware, can actually reorder instructions within a program. So the question is, how can we reason about all the possible interleavings of threads, or the actions of these threads? How can we reason about them based on the different ways or different orders in which they can be executed. So like some example which I went to already is if two threads write to a shared variable, thread A writes value 1 and thread B writes with like value 2, the final value will depend on which order these threads were processed. For example, if it's processed A then B, the value will be 2. If it's processed B then A, then the value will be 1. So this is a big problem. And this problem, like it says, explodes in complexity when the programs grow larger and when the number of threads interacting with the share state also increase. Now, programmers cannot make any assumptions on the relative speed of these threads. We can't predict what the scheduler is going to do, nor can we predict how the different threads themselves are going to operate in terms of their speed of execution. So that leads us to another question, like how can we even debug programs with behaviors that change across different executions or different runs? Now, this brings us to a very important bug, and it's going to be the Heisenberg bug. And that arises when different runs of the same program produce different results. And we've discussed these, like the scheduler might make different decisions, the processor might run at different frequencies across different machines, and another concurrent process may affect the operation. So bugs might arise in one execution or behave in a different manner across different executions. So here we have two definitions or two different names of types of bugs. We have Heisenberg bugs, which are bugs that change behavior or even disappear completely when you try to examine them. So this is like over lots of different runs or multiple executions, some behavior occurs and then sometimes it doesn't. And ball bugs, which are a lot easier to debug, are basically the opposite. These are deterministic bugs. So these are bugs that occur every single time you run the program, this arises. Okay, so that's the difference there. So Heisenberg bugs very frequently pop up when doing multi-threaded programming, which makes sense because it's dependent on multiple factors like the scheduler, the processor, other processes. And the other thing that I mentioned was that modern compilers and hardware actually reorder instructions to improve performance. So you might have a sequence of instructions or code, and because of modern day compilers being rarely optimized, behind the scenes when they're converting it into like machine instructions, they sometimes reorder different instructions for efficiency. Now, I know that sounds very strange, like I thought my programs start at the top and end at the bottom, like I've programmed them. When did this reordering occur? Well, an analogy that you can use to understand this is as shown here. So we walk into a cafe and you ask for something to drink and a sandwich. So you're asking for both of those items. Now the person behind the counter hands you the sandwich, which is right next to him, then walks to the fridge to get your drink. Now the question is, did you care that you were given the two items in the wrong order? Do you care that you got the sandwich first and then the drink? Would you have him rather had gone all the way to the fridge to get the drink first, simply because you had given it in that order? And that's the exact same idea behind compiler and hardware instruction reordering. The idea here is that we do the most efficient instructions first and then do the slower instructions. And we only do this reordering when it doesn't affect the outputs or it doesn't affect the actual execution of our process. So in these cases where you wanted to do one thing and another thing and the ordering doesn't matter. That is what's happening behind the scenes. This is something I didn't even know, but it was interesting to discover. If you want to read up more about it, you can go to this link here. Stack Overflow obviously coming in clutch whenever it comes to problems and questions that no one knows the solutions to. So yeah, feel free to have a little read there. So this reordering is generally invisible to single-threaded programs because it doesn't really change anything. However, the reordering can become visible when we actually start accessing shared states or as a result of our process interleaving. And just like interleaving was when like a process is stopped and another, like a context switch occurs, so another process is started again. That is like a process interleaving. And it's a sequence of like multiple processes being executed. So this reordering becomes a problem in our multi-threaded world. So how do we go about solving all of these problems of interleavings, reordering? Well, we use structured synchronization. And later on, the one specific synchronization technique that we'll be discussing is locks. So given these challenges of our multi-threaded code, which can introduce non-deterministic, non-reproducible bugs, which was our Heisenbugs, how can we solve this problem? Well, a naive approach to these problems would be to have some sort of ad hoc reasoning to the effects of process interleaving. A better approach is to utilize structured synchronization. So what this means is we need to structure our program to facilitate reasoning about concurrency. So the way in which we actually structure our code or the way we develop our program must incorporate some sort of reasoning or understanding about concurrency. And additionally, we need to utilize a set of standard synchronization techniques to control this access to these shared states. So these techniques are what we're going to be looking at today, or one such technique at least, and that is, like I mentioned, locks. So the challenges that these techniques will help us solve are as follows. One is like a race condition, and this occurs when the behavior of a program depends on the interleaving of the operations of different threads. So say we have thread A and B, and again, this is just another example of how this is an issue. Thread A says let x equal x plus 1, and x in thread B, we say x is equal to x plus 2. Now, one like interleaving could be where we do A first and then B, which would look something like we have here in the block, where we process A completely. And this like program here, which is x is equal to x plus 1, would look something like this in terms of our like machine instructions, where we load the value x, we then add our 1 to our register, and then we now store that value back into x. So here we would do this one first and then this one, and we assume that x is equal to 0 in the beginning. So we get a plus 1 here, so 0 plus 1, and we'll have 1 plus 2 here, so that gives us 3. Alternatively, we could have some swapping going on that results in an interleaving that looks like this, where we do the load instruction for thread A first, and then there's like a context switch which makes us load, which results in us processing the load instruction from thread B. So here we basically just loaded the value twice of x, and now currently our value inside x, inside R1 would be 0, and it would be 0 here as well. We would then add 1, so that would be 0 plus 1. And then again here we would have a 0 plus 2. And we would store the values, and this would store 1 here, and then this would store 2 here. So you can see the final result would end up as x is equal to 2. And then lastly we have another one here where the final states or the final x value would be equal to 1. So what a race condition is when like multiple threads are competing with each other to perform or to be executed, and this results in, as you can see, multiple different solutions. Now, one thing that we can actually utilize in order to solve these problems, and they'll be coming up quite a bit, is atomic operations. Now, atomic operations are program operations that run completely independent of any other process. And during an atomic operation, a process can read and write a location during the same data transmission. So what that means is that during this atomic operation, we can perform a single read and write in one time step. So at the same time, basically. In this way, other input-output mechanisms or processes cannot perform memory reading or writing tasks until this operation is finished. So this is a way of saying, okay, I want to specifically finish this task, and during that time, nothing else can actually mess around with my program, and nothing else can read and write memory to this location. So an atomic operation is one which executes as if it were not interrupted in space or time. So atomic operations cannot be interrupted. And some examples of these are load and store. So this idea of an atomic operation is going to come up later when we're specifically looking at lock implementation, because we'll utilize atomic operations to ensure our program is correct. An additional challenge is a problem that's called the too much milk problem. And this models problems of coordinating access between shared memory by multiple threads which only use load and stores. So an analogy or a hypothetical example to the too much milk problem is that you have two roommates who share a fridge. And these are pretty good roommates, and they'll always make sure that the fridge is stocked with milk. Now, one event can occur, or one scenario, and that is where, at 3 o'clock, roommate 1 looks in the fridge, he realizes they're out of milk, and then he decides to go to the store. Now, during this time, roommate 2 comes in, he also looks in the fridge, he realizes that they're also out of milk, and while roommate 1 is already arriving at the store, this occurs. Now, at the same time, both of them decide, okay, well, roommate 1 says, I'm going to go buy milk. And now roommate 2 is saying, okay, well, let me leave to go buy milk. Then roommate 1 arrives back home and puts the milk away, thinking everything's good. And later on, roommate 2, after following the same sequence of events, arrives home and puts the milk that he's bought away. And now you've got double the amount of milk. So this is the too much milk problem. So here you can see that there's a problem that arises when both our threads aren't really communicating with each other. Well, if we only actually have atomic operations such as load and store, is there actually a solution that can solve this too much milk problem that satisfies two conditions? One of safety, that the program never enters a bad state, such as more than one person buying milk, as well as liveness. And this means that a program eventually enters a good state, or you're ensuring that a program will at some point enter a good state. And in our hypothetical, that good state would be that if milk is needed, someone actually goes and buys it eventually. So we're just going to start thinking about naive solutions to how we can solve these problems. And eventually this will lead on to how we start understanding how locks work. So a basic idea we could have is to simply leave a note. So here we have a case where if milk is equal to 0, i.e. there is no milk, then I'm going to leave a note, and if there is no note that's currently been left, then I'm going to leave a note indicating that I want to go buy milk. I'm then going to go buy the milk, and after I've bought the milk, I'm going to set my note back to 0. So this is quite a nice way of communicating between different threads. So that say if someone else comes along and they see, oh, the note isn't equal to 0, so someone must be buying the milk already, so I won't go buy the milk. Unfortunately, this solution can violate safety. And this is again as a result of the different interleavings of processes. So here we've actually created a Heisenbug, which only occasionally occurs based on interleaving, or based on the different ways in which our scheduler will process or schedule our processes, as well as like interrupts and stuff like that. So here we'll say, okay, roommates 1 on the left, and then roommate 2 on the right. So our first roommate says, oh, milk's equal to 0, so I better go buy some milk, right? And then our scheduler says, well, you're done for now. I'm going to then transfer over to, or I'm going to schedule our roommate 2. And he says, well, milk is still currently like set 0, so I need to go buy milk. He's then going to say, oh, well, the note is currently set to 0, so no one's currently buying milk. So I'm going to, change the note, and I'm going to go buy milk, and then I'm going to set the note back, and I'm going to be done. And then the scheduler says, okay, well, he's done, so are there any other processes that need to be scheduled? Well, yes, roommate 1 still needs to finish. And he's going to come in here, but he's already checked the milk is equal to 0, so he'll continue off on this next line here. And lo and behold, the note is 0 because roommate 2 had finished everything and he had set the note back to 0. He's then going to go buy milk again, which is a problem because we currently already have milk. So you can see how in this case we've generated our Heisenbug, and we failed our safety condition. So how can we fix our code now to maybe alleviate this issue? Well, another idea is to have 2 notes per thread, and these can be used to check if another one is contemplating buying milk. So here our thread 1 is node A equals 1, and if node B is equal to 0, then check if there's no milk. If there's no milk, then I'll buy milk. So the idea with node B equaling 0 says that, well, if node B is equal to 0, that means thread 2 or roommate 2 is not thinking about buying milk. And then obviously the opposite occurs for our thread 2. So unfortunately, again, we've solved our problem with safety in the sense that we won't get a case where both people are buying milk at the same time. But we have resulted in a violation of liveness. And that occurs is because it is possible for both threads to check the other's thread note and for both of them to decide to not buy milk. Now, additionally, to solve this new problem is by ensuring, okay, so let me just rewind a bit. How this occurs is if thread 1 is processed up until the end of this line, so he sets his node A to equal 1. Then thread 2 is then scheduled and he processes this first line, which is node B is equal to 1. So now currently both nodes are set to 1. Then if thread 2 say carries on, well, this node A is still equal to 1, so he won't do this. Okay, but then if he's then, while he's contemplating this, or while this is being processed, thread 1 is then rescheduled. Well, node B is still 1, so he won't do this either. So you can get a case where they're in like the gridlock state, where both of them are thinking about it, but because they're both thinking about it, then none of them do anything. Okay, so to solve this new problem, we need to do a slight modification. And that is by ensuring at least one of the threads determines whether the other thread has bought the milk. So instead of both of them looking at each other, the one thread will look at everyone else basically first. So we do this by changing our code up a little bit. So we still have this node A is equal to 1 when I'm contemplating buying something. And now, instead of just skipping this, if node B is equal to 1, we're going to say while node B is equal to 1, do nothing. So it's basically just going to hang here, or it's going to wait until our thread 2 is finished contemplating something. If thread 2 then finishes without buying milk, we'll then exit this because node B will equal to 0 over here. and we will then check if the milk is fine. If the milk isn't fine, we'll buy milk, and then we will then change our node back to 0. So that's one solution which is both safe and live. But it's not efficient, right? Do you really want to have one thread that's just idling away, waiting for all the other threads to do their business? Because of this busy waiting loop, basically. All you're doing is like hogging the CPU and consuming resources. So it's definitely a solution, but it's not the most efficient solution. Now, a better solution is to utilize our synchronization objects to coordinate different threads, to coordinate the access different threads have to the shared state. And that is going to be our locks. So we can use a primitive synchronization technique or object, called a lock. And this is designed to enforce mutual exclusion control policy, meaning that the idea here is that if I have the lock, I'm the only one that can go into this region of the code. And what you have is that only one thread can own a lock at a given time. So here we have a function called by if needed, and it says lock.acquire, and this will only like return true, or it will we'll see later exactly how this works. But if if no other thread has the lock, then I will gain the lock, and then I'll be able to do this next part of the code, this if milk 0 milk plus plus. And then once that's finished, because I've completed my critical region that I wanted to within the lock, I can then release my lock, and some other thread can have access to it if they wanted or if they needed. So that's the idea of locks, basically controlling access to a region of code in essence. So now our locks can be in one of two states, busy or free. A lock, when you create it, it is initially free, meaning that anyone can actually access the lock. No one's acquired it yet. And lock acquire, so this is kind of like a function, waits until a lock is free. So by waits, it's kind of like that looping thing again, but we'll get into the specifics of it. So it waits until a lock is free, and then automatically makes it busy. So if a lock is free, then it basically acquires the lock and sets this a state parameter to be busy. Lock release simply makes the lock free, or changes the state parameter to be free. Now, because of the way it is implemented in this fashion, it ensures a couple different properties. One of mutual exclusion, which is what we really desire, which means that at most one thread can have the lock or can hold the lock, meaning that in our critical region of code, which is surrounded by our lock statements, only one thread at a time can actually perform this task. So that's the mutual exclusion that we're looking for. It also ensures progress, which means that at some point, some threads succeed at obtaining a lock. So if there is an acquire statement, at some point, a thread will get that lock. And bounded waiting. Now, this means that our waiting time is bounded by the number of threads. So this is more of a statistical or complexity analysis type thing. If you have 8 threads, well, the waiting time will be bounded by a factor of that 8. And it's if you have n threads, well, it will be dependent on your waiting time will be dependent on n. Cool. So let's check some code about how locks actually function. So like I was saying, critical regions, maybe you weren't too sure what I meant there, but locks ensure that any critical section executes as if it were a single atomic instruction. So that's that mutual exclusion that we're looking for. So hypothetically, say we wanted to update this balance variable by saying balance plus 1. Okay. Say we wanted, and this was a shared variable, say we wanted to make sure that this can only be accessed specifically as an atomic instruction. So how we do that is, well, we create a lock variable. Right? It's basically just an object or a structure that we define, something like this. So some globally allocated lock. Now, since it's globally allocated, it will be stored on the heap. And then later on, if you want to perform that, or if you want to surround some task, if you want to make sure that a task will be executed as a single atomic instruction, we basically surround it by a lock and an unlock function, where we say lock at the address of our mutex, and we say unlock at the address of the mutex. So this lock function will check if there is a lock available, then I can then move on. It will return from this function, and I can then do this one. If a lock is not available, it will wait inside this function and not continue on. So our lock variable holds the state of the lock. And available, or another word for it would be unlocked or free. That means that no threads hold the lock. And acquired, or held or locked, means that exactly one thread holds the lock and is presumably within its own critical section at that moment. So if I just go back one slide. So if this states that a lock is held, that means that some other thread must be processing this balance is equal to balance plus one instruction. Okay. So our lock function, how it works is that we try to acquire the lock first. If no other thread holds the lock, the thread will acquire the lock, and it will therefore then enter the critical section, it will enter the critical section of that we've defined. Now this thread is said to be the owner of the lock at that time, if it occurs. So other threads are prevented from entering the critical section while the first thread that holds the lock is in there. Specifically for the POSIX library, which remember we discussed a little bit last time, was that Unix-based library, we have a slightly different naming convention for our locks. We use pthread underscore mutex underscore t to define a lock. And this is again used to provide our mutual exclusion between threads. So it works exactly the same as before, but this is more of a specific syntax for implementation. What is interesting is that we may also use different locks to protect different variables. There are a lot of different types of locks that we can implement. And that is what we're going to be looking at in part 2 of this lecture, is implementing various types of locks and where they perform better and worse. So just to finish part 1, we're going to be thinking about building a lock from scratch. So when thinking about building a lock, we need to think of an efficient way of providing mutual exclusion at a low cost. And building locks need some sort of help from the hardware and the operating system to perform its task. We also want to evaluate the performance of the lock by measuring, does it actually provide mutual exclusion? In other words, does the lock prevent multiple threads from entering critical sections? Does it ensure fairness, meaning that each thread has an equal opportunity of acquiring the lock when it is free? Now, if it doesn't, that means a starvation would occur when one thread never acquires the lock and can therefore never finish execution. We saw how starvation was a factor when it came to scheduling, right? Some long processes which didn't have any interrupts or input-output interrupts could suffer as a result of starvation. And thirdly, performance. Now, does the time overheads added by using the lock affect the performance substantially or not? Now, one of the simplest locks that you could think of would be to simply disable interrupts, preventing that context switching or that interleaving from occurring, right? So one of the earliest solutions was to do exactly that. And this was invented for single processor systems. So our lock function would just simply say disable interrupts, meaning that this current process could not be interrupted via some sort of maybe input-output or a context switch in any sense. And then when you were done with the critical section, after basically acquiring the lock and disabling interrupts, you would then unlock and enable interrupts. This kind of makes sense, and this would occur after your critical section. Now, the problem with this is that, well, there's multiple problems really. The first one being that you require too much trust in applications, meaning that a greedy program could essentially monopolize the processor. Now, what if I just simply wrote a program that said at the beginning, like I had like int main or something, and then I said void lock, and then I did everything, and then I unlocked. I could essentially control the processor for the entirety of my program. And what if my program, for some reason, ran like an infinite loop or something like that? Well, I would essentially have control of the processor forever. So that was one problem, right? You had to trust that programmers and applications didn't abuse the CPU in that sense. Additionally, it obviously doesn't work on multiprocessors, right? Because you can still have multiple processors running at the same time on multiprocessor systems. And once again, these processors could still be accessing these shared states and therefore affecting the results of the program. And thirdly, code that masks and unmasks interrupts is executed slowly by modern CPUs. So it's quite a slow process or a slow instruction to execute. So in this very last part of part 1, I'm going to quickly demonstrate why hardware support is needed for implementing locks. And I'm going to demonstrate it through this basic example here. So our first attempt at building a lock is by using a flag to denote whether the lock is held or not. And then I'm going to demonstrate the problems that arise as a result of this. So here we say we're going to initialize some lock, and this lock is going to have is going to be defined by the structure up here, which basically says that you have a single integer flag that we can work with. So then in our initialization we say mutex flag is equal to 0, indicating that the lock is available, which makes sense, right? When you create the lock, no one's acquired it yet because you've just created it. So therefore it should be equal to 0. Okay, so now our lock function would look something like this. While mutex flag equals 1, meaning that the lock is held, do nothing, just spin wait. So the spin wait will become something that will pop up quite a bit, and it essentially means, remember before I indicated that if the lock was held and you couldn't acquire it, you'd basically stay within this lock function. And that's because of this loop here. This says that I can't get the lock at the moment, so I'm just going to wait here and do nothing until it is available. Okay, so while mutex flag is equal to 1, wait. If it isn't equal to 1, that means it must be equal to 0. Therefore, I can acquire the lock because it is available. So if I can acquire the lock because it is available, I'm going to set the flag equal to 1 because I'm taking the lock, so it's held. Even though it's held by me, I must indicate that. And now this function will return, and then I can actually process my critical region. After which, the unlock will obviously be utilized. And unlock simply says, take the flag variable and set it to 0 because I've finished using the lock. So how this looks in like an actual process would look something like this. The reason this is an issue is, one, because of there's no mutual exclusion. Now we assume the flag is equal to 0 to begin with, so neither thread has the lock. What ends up happening is I call lock, and that says while flag's equal to 1, and then while this occurs I then interrupt and switch to thread 2. So before I have a chance of actually acquiring the flag or acquiring the lock by setting the flag equal to 1, I get swapped out. Then thread 2 says, well, I'm going to call lock while flag's equal to 1, while it's equal to 0. I didn't get a chance to change it. So this is false, so I'm going to then move on and set flag equal to 1. So now I've acquired the lock, and when I do this, I then get swapped out again. And what ends up happening now is that thread 1 starts processing, and it had already passed this while loop statement. So it sets its flag equal to 1 because in its eyes, flag was currently 0. So both threads think they have the lock now. They both set the flag to equal 1. So obviously it didn't ensure mutual exclusion. So problem 2 that arises is that spin waiting wastes time waiting for another thread. So what if I did actually set the flag, acquire the lock, and then begin processing my critical region? Well, thread 2 then would have to wait for however long I had to do my processing, and that's also an issue. So we therefore need an atomic instruction which is supported by hardware. And this is called the test and set instruction, which is also known as the atomic exchange. And this is what I'm going to be talking about in part B, the test and set instruction. And this will help to ensure both our mutual exclusion and decrease our waiting time. So thank you all for listening, and I'll see you in part 2.